All right, let's go ahead and do a high-level pass on Chapter 4. Chapter 4 is all about integration. So basically, we're starting, in some ways, the second half of calculus. Because all of calculus, this calculus you're going to see, is about two things: differentiation and integration. I told you at the beginning of the year, all of calculus is about two things. You remember what the first thing is? Not differentiation, but area was the second one, and slopes was the first one. And now we're at the area part. So slopes and areas, really everything boils down to. So let's go ahead and do a high-level pass here on Chapter 4. So it's about integration. You can see there they've got an awesome picture of the jet plane with the shock wave from the sonic boom occurring there. It's actually compressing the air, which is changing the condensation point, which is making it form a cloud, if I understand that anyway properly. So let's see here. So 4.1, antiderivatives and indefinite integration. So every student loves 4.1 because it's just such a fun little lesson here about reversing your thought process. We can see some graphs up. Then 4.2 is going to talk about area. And we're going to build this upon the idea of the limit. So you'll see a little bit of limit stuff there. That's okay. All of calculus is based on the limits. Somebody tell me, what's 4.3 about?
Riemann sums and definite intervals.
Yeah, sometimes say Riemann, sometimes say Riemann. And so Riemann sums and definite integrals. So something about sums, adding some things up, and then the definite integral, which we will definitely look at that very closely. Somebody else, what's 4.4?
Fundamental theorem of calculus.
Fundamental theorem of calculus. Isn't that weird? It takes 4 chapters and 4 lessons to get to the fundamental idea of calculus. I think they would have got that been like lesson 1. But you know, whatever. Seriously though, the fundamental theorem of calculus connects the derivative with the integral. And so this is where it makes perfect sense to put it right here, because if you just tell it to students at the beginning, then they have no idea. We'll talk about something called the mean value theorem for integrals, which is the 4th theorem that you need to know. Then the second fundamental theorem of calculus, you see that? It's kind of, it always gets like secondhand treatment. That's on page 288. It's not even like, it doesn't get its own section. And it's also kind of an interesting sort of joke. It's like the fundamental theorem of calculus, and then the second fundamental theorem. It's like, wait a second, which one's more fundamental? Which one's the basic, right? It's sort of like, you know, there's, you know, only one rule, but there's another equal to it. You know, okay, well, I think some wise person said that, so I'm not going to disagree there. All right, 4.5, integration by substitution. So we're going to start getting to some advanced integration methods. Basically everything that we do with derivatives, we're going to do the other way, now with integrals. All right, so we had chain rule, now we're going to have like reverse chain rule. Okay, we had product rule, we're going to have something called reverse product rule, although that's not for like another 2 chapters. Okay. Do we have a 4.6?
Yep.
Numerical integration, okay? This is trapezoids, and actually this is a good kind of way of ending it, and that's all of Chapter 4. And then we get to Chapter 5, which is logarithmic, exponential, and other transcendental functions. This textbook is what's called a late transcendentals approach to calculus, believe it or not. Calculus is so old that there's actually different theories on how to teach it. Some people are like, wow, we think that you should teach it with transcendental functions early. And then people are like, we think you should have like before integrals or before all this stuff. And then people are like, well, we think you should have it afterwards or later. So that probably means, you know, for y'all, just don't worry about it. But for as a teacher, this is the stuff that we like. When calculus teachers get together, we have like knockdown, drag out fights. Not about politics, not about religion, but about early or late transcendentals approach to calculus. So there you go, a little inside baseball. All right, so let's go ahead and skip back there to 4.1, antiderivatives and indefinite integration. Teek, go ahead and read to us those 4 items there. I'm looking at the top of 248. those are the 4 objectives. You read that out loud while the rest of us follow along. Go ahead.
You said which one?
Those bullet points.
Okay, write the general solution of the differential equation. Use the undefined integral notation for antiderivatives. Use basic integration rules to find antiderivatives. Find a particular solution of a differential equation.
Alright, so the big picture for today is to start thinking backwards. If you think through your entire math career, anytime you finally got a handle on something, the teachers made you do something the opposite way. Okay? So as soon as you got addition down and you're like, I got this thing addition mastered, it's awesome. What did they teach you? Subtraction. And you're like, and which one's always harder? Subtraction, the second one. Okay, you're like, all right, I got this subtraction. Then they're like, okay, multiplication. And then division. And which would you rather do, multiplication or division?
Multiplication.
You'd rather do multiplication, right? Because the second one was harder. And then you taught, like, they taught you like squares, and then you had to do like square roots, right? And they taught you functions, and you had to do inverse functions. You had to like sine, cosine, tangent, then you had inverse sine, inverse cosine, inverse tangent. Okay, so we've done the whole derivative thing. Now we're going to do the antiderivative thing. All right, and as you can expect, it can be a little bit harder in some cases. So 4.1, this is the antiderivative. And sort of the formal name for the antiderivative, indefinite integration. Right? Indefinite means it's not completely defined. There's a little bit of fuzziness, a little bit of ambiguity there. All right. And I'll show you right off the bat why there's a little bit of ambiguity. Let's say you have a function y equals 2x. Awesome, great. It's nice and linear. Let's take the derivative of that. Y prime equals 2. Any questions?
Nope.
Great. So let's just go the opposite way. No big deal. What if oh, sorry, Y prime. So, alright, so today's lesson, we're going to start with y prime equals 2. Let's go this way. What is y? 2x. Oh, that's not very difficult, except that it's wrong. Well, it's not totally wrong, but actually it's just incomplete. Because if you tell me that the derivative is 2, there are actually a couple other answers that would be accurate for the original function. Okay? Can anybody think of another function that could be up here whose derivative would be 2? 2x plus 1. But wait, there's more. It's just like a bad infomercial. Alright? Levi, since Osmani robbed you here, what's another one?
2x plus 2.
2x plus 2.
It's like the mean
2x
there for
minus
the second.
1. Yeah. So, anybody else want to venture a guess on another one?
2x minus
2x. Ooh, I like it.
That's nice. Genius.
You did not go with the obvious. You know, that's the rule of 3s for jokes. Okay? You have one just to set it up. Okay? Then you have the second one to set the pattern. And then you have the third one to turn the elephant inside out. Alright? But no, that's really what it is. It's like a rule of 3s. That's why there's always 3 guys walk into a bar, or 3 people are stranded on an island. You know what I mean? There's always it's a rule of 3s of jokes. There's all kinds of rules. There's the rule of 3. So he did the rule of 3. He said 2x. He didn't say plus 3. He said minus 1. Okay? In fact, how long could we continue this fun activity? We could go on infinitely. We could put whole numbers. We could put decimal numbers. We could put like y equals 2x plus 1.1, or y equals 2x minus 7 halves. You know, all sorts of different stuff there. And so that's why the most technical, complete answer would be, you must have had a teacher who taught you some of this, I guess.
Class infinity.
Y equals 2x, must have been pretty good, I guess, yeah. 2x plus c, that is the most generic form. So this is why it's called indefinite, because it's not defined. This c right here is called the constant of integration. And we have a formal way of writing about this. For instance, when we wanted to take the derivative of something, we would say, the derivative with respect to x of 2x. I don't like that one either. Is equal to 2. That was apply the differentiation process to 2x, which, if you remember, the actual differentiation process was the limit of the difference quotient, the limit of, f of x minus f of x, or f of x plus h minus f of x, delta x, all over delta x, blah, 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 so on and so forth. That's the formal way of writing it. We do have a formal way of writing, find the antiderivative, and that is this. We would say the antiderivative of 2, and then we write a dx there, and we say with respect to x. So, in words, this whole thing would be the antiderivative of 2 with respect to x is 2x plus c. This sort of elongated S shape is the integral symbol. Whatever's in between that and the dx is called the integrand. And then that dx right there is going to tell us what is our variable of integration. So here in a second I'll show you what would happen if it was a different variable. The other way that you can say this, rather than saying the antiderivative, you could just say, what is the integral of 2, and you can just even say dx if you want to. So just to change it up slightly, you can have the integral of 2 dt, and that means that t is our variable of integration.
2t plus c.
2t plus c. It just means that your variable here happens to be t, and you could have anything else that you want to do. So pretty much a lot of the rules that we were familiar with derivatives will now apply to the antiderivative process. So if you remember the power rule for derivatives, what's the power rule? The derivative with respect to x of x to the n was pop down, power down. So n times x to the n minus 1. What we're going to do now is sort of figure out what is the anti-power rule. So So for instance, what if you have the integral of x, what's over here, x cubed dx. So what we want to think through is what would this be, the original function? When I took it, I would have x cubed. Okay? Well, if there's an x cubed here, then up here I would have to have x to the what letter?
Fourth.
Yeah, x to the fourth. Alright? So I definitely know it's going to be x to the fourth. The problem is if I just leave it like that, I say, okay, let's take the derivative of x to the fourth. Well, the derivative of x to the fourth, I have to pop down the 4, right? So it would be 4x cubed. But I don't have 4x cubed, I just have x cubed. Okay? So, say that again?
4 to the 4, or x to the 4 over 4.
X to the fourth over 4. So if I would, for instance, have this, x cubed, okay, then if I divide it by 4, then it would end up canceling out. So I'll make it right down. So x to the fourth over 4, put it right up there. So if I take the derivative of that, the 4 pops out down here, and then it's over 4 from here, and so then those would cancel, and I would just be left with x cubed. So the integral of x cubed dx is equal to x to the fourth over 4 plus c. What if I have the integral of x to the 7th dx? Now you can't answer Levi and Kim since y'all did that last time. So we're looking for what's inside the mystery box here. Let's just see if I can. I've got x to the 7th down here. Since this is an x to the 7th, I know the thing that's above it, the original function, would be x to the 8th. But if it was just x to the 8th, then I would have an 8 that's going to stick out here. So I say, okay, it's x to the 8th over 8. And then if I would do that, then my derivative would be 8x to the 7th and then over 8. And those would cancel and I would have x to the 7th. So x to the 8th over 8 plus c. Are y'all beginning to see a pattern here?
Mm-hmm.
All right, let's see if we can generalize that pattern. Yes? Sure, go ahead. More about hall pass. They're all reads. So, the integral of x to the n dx would be, anybody have an idea? How to generalize this? Levi, you got an idea for us?
X to the n plus 1
Oh, I asked Levi, but okay.
over n plus 1.
But wait,
Plus c.
plus c. Okay, so that's not too terrible now, is it? It's just going the opposite way. Normally, it doesn't cause you problems until like a week or two from now when you're doing derivatives and then you're doing the integral and you're getting switched up, figuring out which one is which. Okay? But for now, it's a happy time. So you may be thinking, what in the world does this have to do with area? And the answer is everything. But for right now, it's nothing because we'll talk about area on Monday. With the derivatives, see if y'all remember this. The derivative with respect to x of any constant times a function. This was what we called the constant multiple rule. You remember what was the derivative with respect to x of cf of x?
CF prime.
Yeah, there's cf prime of x. And for our purposes right now, if you have the the integral of c times any function of x dx, then the antiderivative of that is just going to be c times, well, let's see if we can make this clear. I'm going to put f prime right there. How's that? How does that make sense? If you have c times the derivative, then it's going to be c times that original function.
Plus C and then plus C.
And then absolutely, plus, I'm going to make this a big C so that it's c, that it is different from little c. See? Did y'all see that?
Yes.
Yes.
Oh, I
C.
know you missed it.
Just say C.
There you go. All right.
I envision it.
So, okay. Also, trig functions.
Oh, alright.
The derivative with respect to x of sine was cosine. So therefore, the integral of cosine x dx is equal to sine x plus c. You're catching on. The derivative with respect to x of cosine x was negative sine x. So now I've got a decision. Do I want to put negative sine x inside here, or do I just want to put sine x just for fun?
Negative cosine.
It's going to be negative cosine.
Plus.
Right. You're like, I'm not sure I get that. Why is it negative? Well, this is the great thing about tonight's homework as well. Just take the derivative, okay, and check your work. So it's sort of like, great, now we're at the stage where to check your work, you'll just review yourself on everything you've done in chapters 1 through 3. So I think it'll be fun. So if you're not sure, just take the derivative. The derivative of anything with a negative up front will be negative. The derivative of cosine is negative sine, and the derivative of a constant is 0. So negative times negative is positive, so that's sine x, which matches what we had in there. So just as a reminder, big C stands for constant, which means just a number. Okay? It's not a variable. Okay? If it's a variable, then it could change, it could vary. But big C means it's a constant. It means it's a number like 35 or 42 or 77 or 3.14. Okay? I mean, or pi. You know, even irrational numbers are constants. It just means an actual factual number. And I could continue on this process for, you know, the derivative of tangent is secant is secant squared. So therefore the integral of secant squared is tangent. Okay?
Is it squared?
Yeah, it's been a good Thanksgiving breakfast. Okay. There's a couple other things we can talk about. One is rewriting. So for instance, 1 over x cubed dx. Just like when we had all our derivatives that we were learning, you had to rewrite some of them. We're going to have to rewrite some of these. So at this point, really you're limited to anything, you know, that's just going to use the power rule. So that's a ratio, 1 over x cubed. We want to rewrite that as x negative 3. And then remember your integral power rule. So this is going to be x to the negative 2 over negative 2 plus c. If you want to clean that up and put the negative 1/2 out front, put this in the denominator, you could put negative 1 over 2x squared plus c. You could do that. Bring that x down there. When you're checking your work in the back of the book, they may have this, they may have this. Sometimes there's no rhyme or reason. The antiderivative of the square root of x. Rewrite it. X to the 1/2. So that's going to be x to the, so it was always pop down, power down. Now it's like pop up, 3 over 2, and then divide by 3 over 2.
So it's multiply by 2/3.
Correct. And you might be able to be good enough where you're like, oh, I got this. I don't even have to write that divide by. I immediately know that I'm going to, instead of divide, I'm going to multiply by the reciprocal. That's okay. Some other rewriting situations that you will encounter. Integral of x plus 1 over the square root of x dx. Anytime you have like a binomial or a trinomial over a single term, you can always split it up. The integral of x over the square root of x plus 1 over the square root of x dx.
Why can't we just, like, we just change x, put square root of x to, x to 1/2 and just have them multiply?
Multiply. Yep, you could do that. That would do. That would work as well. Write it like this: you would have 1 minus 1/2, so that's x to the 1/2 plus x to the negative 1/2. And then you would pop up.
Hey, what about the, I'm confused by the first one.
X over square root of x. That's really x to the first. This is 1/2. That's x. That's x to the first over x to the 1/2, and that's x to the 1 minus 1/2.
Okay.
Yeah, sorry, I kind of skipping through that real fast there. So antiderivative, and sometimes you want to put parentheses around the whole thing just to make it clear what you've got going on. And I'm not gonna, we'll see this later, but there is a sum and difference property of integrals, which you basically, if you have a function plus another function, you can just take the antiderivative of both of them separately. So the antiderivative of x to the 1/2, we saw that a second ago. That's x to the 3/2 times 2/3 plus x. I've got a negative 1/2. I'm going to add 1 to that, so that becomes a positive 1/2. Multiply by the reciprocal, so it's multiplied by 2 plus c. And then you could modify that or just leave it as is. It's your call. All right, a couple other things that you might need to do. So you've got something like sine x over cosine squared dx. You may need to manipulate a trig expression a little bit to be able to get it into something that you can take the integral of. Okay? So right now, the only things that you can take the integral of are, you know, we could take the integral of sine or of cosine. What's the derivative of tangent? Instead of
Secant squared.
secant squared. The derivative of cotangent is cosecant squared x. The derivative of secant,
Secant squared tangent, or secant squared tangent.
there's no square, it's just secant x tangent x, and the derivative of cosecant is
Negative cosecant
negative cosecant
for tangent.
tangent. I'm not messing with the negatives there, but these are the things which right now we can handle inside the integral statement. Okay, we can't handle something like that, so we need to manipulate this to resemble one of these. You might use some of the Pythagorean identities from the beginning of the book. Cosine squared could be written as 1 minus sine squared. In this case, I already know what's going to happen, so I'll just show you. You can split it up as sine x over cosine x times cosine x, which you could rewrite that as sine x over cosine x times
Tangent time.
1 over cosine x. Yep. Which is the integral of tangent x times secant x. And that's in my list of approved integrands. The antiderivative of secant x tangent x is secant plus c. So you might want to scroll those down somewhere. These are the only things at this point, the only trig functions. You say, what about if there's tangent in it? What if it's the integral of tangent x? And the answer is, we'll figure out that when we cover transcendental functions in chapter 5. So we don't even have to worry about that. There's some things that we cannot handle just yet. What about the integral of cosecant? Same thing. We're gonna need to know transcendental methods. Same thing for secant. The only basic trig functions that we can have as an integrand are just sine and cosine. Everything else is going to be, squared or some sort of product. So, on some of the problems for homework, you will need to do a little bit of manipulation like that. Okay. Any questions so far? I know this is a lot of stuff, but y'all just fly through this stuff. Let's get to the problem. Any questions so far? Okay. So turn in your book to page 253. If you look there, look at that graph there. That is the graph of some of the solutions to the equation. So if you look here, this says y equals, in the right-hand side of the screen, page, y equals the integral of 3x squared minus 1 dx. All right, they've gone to the trouble of integrating that. It equals x cubed minus x plus c. And they said, hey, I got an idea. For these students, let's show them what happens if c equals 4. And so they graphed that up there. Boom. It's on the very top line in gray. They said, what happens if c is equal to 3? Well, it's going to be shifted down a little bit. What happens if c is equal to 2? And so you've got that curve. What happens if c is equal to 1? And you've got that curve. C is equal to 0, negative 1, negative 2, negative 3, negative 4. Do y'all see what's going on there? That c, that constant of integration, changes whether or not the graph is shifted up or down. And it could be at any place in between those. It was nice of them to choose some integer values, but they could have continued that process indefinitely up to positive infinity and negative infinity, but then we wouldn't be here because they'd still be printing the book. Okay? So what you're looking at there, those are the, all sorts, each one of those is called a particular solution. Okay? The general solution has the plus c, but each of those are particular solutions. If you're going to find a particular solution, then you've got to be given a little bit more information, okay? And it turns out that the little bit more of information that you need is just 1 point, okay? In this problem, do you see up there on the in quadrant 1, they have the point 2,4, and how there's a dot on there? All right, it's a little bit advanced for us, but as it turns out, only one of those curves is going to go through 2,4. Believe it or not. Only one of them is going to actually go through the point 2,4. All the other ones are going to get close to it, they'll pass it, but only one of them is actually going to hit 2,4. And if you have that extra piece of information, then that's going to lock in which graph, which of those particular solutions is the correct one, okay? So that's called an initial condition. That's poorly worded. It's not an initial condition unless it's actually like at time 0. That is a condition. It's an XY pair that will give you the added information that you need. If you look down here below at the next one, on example 7, it says find the general solution of f prime of x equals 1 over x squared when x is greater than 0, and find the particular solution that satisfies the condition f of 1 equals 0. So first they found the general solution. They took the integral of 1 over x squared. The next line you can see they turned that 1 over x squared into x to the negative 2. Did the did the power rule there, integrated x to the negative 1 over negative 1, and rewrote that as negative 1 over x plus c. And then to find which, if you look over in the graph there, they graphed multiple particular solutions. C equals 4, C equals 3, C equals 2, C equals 1, 0, negative 1, negative 2, negative 3. All those different, I guess from a perspective, graphs. But then they said, all right, what if you have the particular point f of 1 equals 0, which means if you plug in an x value of 1, then your y value is 0. So they did that. They said f of 1 equals negative 1 over 1 plus c. Set that equal to 0. Do the math. Comes out to be c is equal to 1. So the particular solution is f of x equals negative 1 over x plus 1. Where they replace that c with the actual value. And as you can see on the left margin, that particular solution, which is the answer, is in bold. They've got that one scrapped a little bit. Okay? Let's do one of these together, which we have to go all the way to page 256, problem number 48. So they say dy over dx is equal to 2 times x minus 1. Says find the equation y given the derivative and the indicated point on the curve. So they give us dy over dx equals 2 times x minus 1. Another way of writing that, you could say, that's like saying y prime is equal to 2 times x minus 1, which that would equal 2x minus 2. They want us to find first the general solution and the particular solution. Maybe that solution there, a little bit of chemistry, when you have the point 3, 2. So you could say the integral antiderivative of 2x minus 2 dx is going to equal 2x squared divided by 2 minus 2x. Why am I putting an x right here? Antiderivative of 2 is 2x plus c. So that means we have y equals 2 over 2 cancels, x squared minus 2x plus c. That is the general solution. The particular solution says plug in 3 for y, plug in 2 for x, and figure out what c is. Okay? So plug in 3 for the x. So I said that wrong. So 3 squared minus 2 times 3 plus c equals 2. So it looks like 2 equals 9 minus 6, so that's 3 plus c. Subtract 2 from both sides, turns out c is equal to -1. And now I can get the particular solution, y equals x squared minus 2x minus 1. That is the particular solution. Alright, your homework are problems 5 through 47 odd. That's a total of 22 problems. That will be due on Monday. Since tomorrow is our quiz, I recommend that you study for this quiz. It involves data with derivatives, maybe some optimization stuff, motion, and approximations of the tangent line, all things that were on that review. Okay. Today we talked about the antiderivative and the integral. And there's the bell. Ding, ding, ding.